A modern news feed is a personalized, constantly updating stream of content. It serves as a dynamic, chronological view of a user's entire network graph. Two core interactions define this system. First, feed publishing, where a user creates and shares a post. Second, feed building, where the system aggregates and presents updates from that user's connections. The system supports various data formats, including text, high-resolution images, and video, all organized in a reversed chronological order, without complex algorithmic ranking. From the user's perspective, these interactions are instantaneous. This perceived speed hides a massive back-end operation coordinating across a fractured infrastructure. The simplicity of the front end is a design choice that masks one of the most difficult scaling challenges in modern system design. The engineering difficulty is a product of the scale. Our target is to maintain high availability for 10 million daily active users. This volume is compounded by network density. In the system, each of those 10 million users can maintain up to 5,000 distinct connections. A naive approach would rely on a real-time SQL join query. Every time a user opens the app, the database would have to perform complex sorting and filtering across 5,000 different connections simultaneously. However, feed retrieval must maintain sub-second latency. Performing real-time computation at a 10 million user scale makes that latency target impossible to hit. To survive this level of traffic, the architecture must move away from real-time generation in favor of extensive pre-computation. To eliminate real-time bottlenecks, the architecture splits at the API layer. Creating a post and retrieving a feed are handled by two separate independent logic streams. Tracing a new post, a request hits the load balancer, web servers, and post service for database storage. The fanout service then asynchronously pushes the post ID into every connected friend's newsfeed cache, while the notification service alerts them. The act of publishing is the starting point for a massive asynchronous downstream data replication pipeline. On the read path, the requirements are different. When a user opens the app, they expect their feed to be ready immediately. Following the retrieval flow, the request passes through the load balancer directly to the newsfeed service. Isolated from the main databases, it fetches precompiled post IDs from the newsfeed cache. With data organized in memory, the system achieves O1 retrieval speed. Heavy media files like images and video are managed separately. They bypass this core logic and are served directly from a content delivery network, or CDN, for faster global delivery. The read path is optimized for speed, delivering a pre-assembled feed list with no heavy computation required at the time of the request. Bringing both paths together illustrates the inherent asymmetry of the system. The write path is highly fault-tolerant because it is asynchronous. If the fan-out process takes several seconds to complete, the delay is invisible to the user. The read path is synchronous and highly sensitive to lag. Any delay in the feed cache is immediately experienced by the user as a performance failure. If the newsfeed cache is empty or fails, the system must cross over and query the main database to hydrate the feed manually, a process that is both slow and resource-intensive. Enterprise scale requires a complete decoupling of these paths, ensuring that write-heavy operations never block the synchronous read requests. This push-based model is highly effective for standard users with average connection counts. However, we must consider the impact of an extreme edge case, a celebrity with 50 million followers publishing a new post. Attempting to push a single post to 50 million individual caches simultaneously will create a traffic spike that can crash the fan-out service. In distributed systems, this is known as the hotkey problem, a scenario where a single piece of data causes a disproportionate load on specific nodes. Solving the hotkey problem requires a hybrid architecture that incorporates pull-based retrieval. We will deconstruct that specific solution in Part 2.